let me show you guys the most legit way to solve the integral of e power of ax times sine of bx dx and the integral of e power of ax times cosine of bx dx. Now the most legit way that I'm talking about is using complex number. Why? That's because you can use the Euler's formula to simplify. Because we got sine and the cosine, inside the sine and cosine we got the same thing, which means I will let z equal to the integral of e power of ax times sine of bx dx plus the little I, the imaginary number I, times the integral of e power of ax times the cosine and this is sine. So I'm sorry guys, sometimes careless mistake. Okay, now we got like this. Since I is an imaginary number, so we can just treat it like a constant, and then since these two, and then we can group them together. So I will have the integral of e power of ax times cosine of bx plus the little I times e power of ax times sine of bx and then dx. And then what we can see right here is we can factorize the e power of ax out. So I will have the integral of e power of ax times cosine of bx plus I times e power of I times sine of bx dx and then close bracket of course. And then look at what we have here. We got cosine of bx plus I times sine of bx dx. And remember there is something called the Euler's formula. So what does the Euler's formula do is when you have e power of ix is equal to the cosine of x plus I times sine of x. So this is the Euler's formula, and then we are going to apply the Euler's formula to here, because as I can see I got two inputs which is bx, so the z is equal to the integral of e power of ax times e power of I bx dx. And what we can see is we can apply the law of indices and then factorize the x out. So it is still equal to the integral of e power of a plus bi times x dx. And we got this thing. This thing is we got the integral of e power of a plus bi times x dx. And we can treat the imaginary number I as constant. Then we can actually easily solve this integral, which is equal to 1 over a plus bi times e power of a plus bi times x. And then what we can see is a plus bi, the imaginary number I is in the bottom, but I want it at the top. We can do that by multiply its conjugate. And by multiplying its conjugate, because I multiply the conjugate at the bottom part, make sure I have to apply make sure I have to multiply the same thing at the numerator to make sure the expression is equivalent to each other. And then we can expand this, then I will have z is equal to a minus bi over, now this one, remember the difference between squares formula. So a square minus b square is equal to a plus b times a minus b. Then this one is equal to a square minus I square times b square, and I square is equal to -1. So a square plus b square, and then times, and then we're going to expand the e power of ax times ibx. Why are we going to do that? That's because, now look at here, because we already solved for z, then we can express it once again with this. So e to the power of ibx is going to be equal to e to the ax over a square plus b square times a minus bi times cosine of bx plus I times sine of bx. And then we can expand the multiplication between these two expressions, which is a minus bi times cosine of bx plus I times sine of bx. So z is equal to e power of ax over a square plus b square. Now, so in the expression then I will have a times cosine of bx plus ai times sine of bx minus bi times cosine of bx, and we'll multiply negative bi times I is going to be plus b times sine of x, sine of bx. And then what we are going to do is we are going to group with one of it. We want to group the expression here in form of a plus bi. So z is equal to e power of ax plus a over a square plus b square times a cosine of bx plus b times sine of vx plus the letter I will write like here, I'll write right here, plus the letter I times a let me see, times a times sine of bx plus b times cosine of bx, and then put a bigger bracket, a bigger. Now if we can imagine that we can expand the e power of ax over a square plus b square to here, right? But now we can imagine like that. Now let's talk about the real part and imaginary part. Remember, what is the z? The z is the integral of e power of ax times cosine of bx dx plus the letter I times the imaginary number times the integral of e power of ax times sine of bx. And the final solution we got here is e power of ax you can see is the e power of ax times a squared plus b squared. If we expand it individually, we will get the same same situation as the initial one. That's because if we compare the real part and imaginary part, we will get the integral of e power of ax times cosine of bx dx and the integral of e power of ax times sine of dx dx. So the real part of z is equal to the integral of e power of ax times cosine of bx. Now if you try to expand this, you can, but in the end it's still same because we can just imagine it, which is equal to e power of ax over a squared plus b squared times a times cosine of bx plus b times sine of bx. And the imaginary part of the z is equal to the integral of e power of ax times sine of bx, which is equal to e power of ax over a squared plus b squared times a times cosine of bx. Sorry, it should be a times sine of bx minus y plus y plus. Okay, so y plus. Sorry, my mistake. So and then minus b times sine, no sine anymore, cosine of bx. Why do this? Just small mistake. So this is the solution for these two integrals, and we are done. Oh my god, so this is how you apply the complex numbers to solve some specific integral. Now you can use complex number when you have a cosine and the sine getting the same input. Now even though you just have only the cosine, but you can try to create another integral for it's like for you can try to create another integral such that it will meet the Euler's formula, and then you simplify. So this is how you apply complex numbers to solve the integral, and this is one of the examples. Oh my god, this is quite complicated. And as always, if you guys enjoyed this video, leave a like and subscribe to my channel for upcoming math videos, and I will see you guys next time.